today we are going to learn antiderivatives. This is the first section of college calculus. After this section, we learn different techniques of antiderivative and the applications of that. So this section is very important to understand the concept. This section has 3 examples where we discuss applications. First of all, I would like to give the motivation. Let's consider this example. Let's say you are given a function g of x, 10x plus 3, and then you know how to get the derivative of that. That is g prime of x, which is 10. So this is what you learn in Calc 1. Now, if I ask this question from you, how do you answer? The question is, find f of x such that f prime of x equals 10. Right? So this is the question I have. Okay, so what's the answer? So you have to find f of x such that f prime of x is 10. In this case, your f of x is actually 10x plus 3. Right? So how do you understand that? By using your Calc 1 knowledge. If gx is 10x plus 3 and the g prime is 10, now you are given the g prime, which is 10. G prime here is actually f prime, which is 10. So you are going reverse. In this case, you are going reverse from here to here. Okay, you are going here, reverse from here to there. Right? In that case, you say like your f of x is 10x plus 3. So this is known as antiderivative. This is known as antiderivative. Now I'm going to give you the definition of antiderivative. When I write like DEF superscript n, that means definition. I use that symbol or that abbreviation to denote definitions. Let's have the definition. A function uppercase f is called an antiderivative of lowercase f on an interval I if f prime x, that is uppercase f prime x, equals lowercase f of x for all x in I. I don't know whether you are familiar with this notation. This notation is from set theory. how do you read this? This means an element of. An element of. When you say like x, that symbol I, that is read as x is an element of I. This is same as x is an, let me take this here. X is an element all right. Element is stand for a member, or you could say x is a member of I. If I write a little bit more, let's say your family has 3 people. Your dad, who is Tom, and your mom, Jenny, and you. And let's say this is your family, and you could say you, Vivi, is a member of this family, right? Vivi is a member of Tom, Jenny, and Vivi family. It's very simple. That's how you represent an element from a bigger set. All right. And this is the definition of the antiderivative. Let me read it once. A function f is called an antiderivative of f on an interval I if f prime of that is f of x for all I in x. All right, so this is the definition of antiderivative. So let me write a little bit more here. You might have this question in your mind. Is the antiderivative is the antiderivative of a function is unique. Okay. So in math, we sometimes worry about the uniqueness. The question is the antiderivative of a function is unique. I don't know what answer you have. I can show you some results, then you can determine whether it's unique or not. All right. Go back to the previous example. Example number 1. In example number 1, we found f of x such that f prime of x is 10. Right? In that case, you gave me the answer like f of x should be 10x plus 3. Okay, 10x plus 3. Once you get the derivative of 10x plus 3, you can get 10. the derivative of this one is that. If you get the derivative of that, you get that. This question is asking whether this quantity is unique in order to get that. Okay, this question is asking whether that quantity or f of x is unique in order to get that. That is not true, right? Here I wrote f of x equals 10x plus 3. In the next time, I am writing f of x equals 10x plus 100. I wrote f of x equals 10x plus 100. Now what's the derivative of that? The derivative of x should be let me take this out. That should be 10. All right. So in that case, 10x plus 100 is also an antiderivative of 10. All right. So let me think about another function. Now I'm writing f of x equals 10x minus pi. The derivative of that one should be 10. Here 10x minus pi is the antiderivative of 10. So let me put a small note here. We see that we see that let me put like f prime x f prime x equals 10 has several antiderivatives. Okay, it has several antiderivatives. So the conclusion is it is not unique. Okay, let me write that. Antiderivative is not unique. Okay, if you recall your memory, derivative is unique. Derivative is unique. For a given function, you have only one derivative, but antiderivative is not unique. For a given function, you can find several, or if I talk precisely, you can compute infinitely many antiderivatives. Infinitely many antiderivatives. Okay, because of that reason, let me modify the definition of antiderivative. In the next line, I'm going to modify the definition of antiderivative. So the new definition, okay, this is the definition of a general antiderivative. Let me write this. This is the general definition of general antiderivative. General if f is an antiderivative of simple f x on an interval I, then the general antiderivative of simple f of x on the interval I is, so what is the general antiderivative now? Can you think about that? So, and you know that antiderivative is not unique. Let's say you are given f prime x equals 10. So it has plenty of antiderivatives. The first antiderivative that you could think is 10x plus 100. Previously we thought it to be 10x plus 3. And then we thought it to be 10x plus 100. And then 10x minus pi. You can think plenty of such antiderivatives. Actually, infinitely many, like 10x plus 1000, 10x plus million, 10x minus log 10 to the power 5. Right? You could think of you can think plenty of such antiderivatives. So what should I do? Because of that reason, here I put the corresponding antiderivative is f of x plus c. I put a constant to denote all the constants, where c is a constant. All right, this c is a constant. That's very much important. You have to make sure that you introduce this constant in every problem you solve. Otherwise, it will cause to lose points. Let me take these points out. All right, now let me write a little more. First point that I have to specify here, general antiderivative is the indefinite integration that we learn later in this class. General antiderivative is the indefinite integration. All right, indefinite integration. We have two types of integration: indefinite integration and definite integration, that we are going to learn later in this course. Okay, so let me for now let me put a small note. Otherwise, you might be confused. There are two types indefinite integration definite integration. Okay, this is extra. All right. Let me talk about the notation for indefinite integration. The notation that we use is like this. Let's say you're going to compute the indefinite integration of the function f of x with respect to the variable x, and then you introduce this symbol. This is a symbol, and then you write dx. This x is called the variable of integration. All right, this function is called the integrand, and this symbol is the integral sign. All right. We are moving to the next topic in this section, that is rules of antiderivatives. Rules of antiderivatives. I'm sorry. Antiderivative is same as integration. Just keep that in mind. Integration, antiderivative are same words. Okay, let the antiderivative of f of x equals the antiderivative of lowercase f of x equals uppercase f of x, and the antiderivative of g of x, the lowercase g of x equals, I'm sorry, that equals uppercase g of x. All right, so this table gives you rules of antiderivative. First we have different functions, and then we have the corresponding antiderivative. So this is the first column. And that's the second column. All right, let's consider the first function is c times f of x. Keep that in mind, this c is a constant. This c is a constant. Let me put it here. Here, c is a constant. C is a constant. The antiderivative of this one should be, actually this is a function multiplied by a constant, so you can just keep the constant out and then get the antiderivative of the function itself. All right, so you know the antiderivative of the function f of lowercase f of x is uppercase f of x, and then since you have a constant in front, you can just multiply uppercase f of x by that constant. Nothing will happen to the constant when you get the antiderivative of a function. All right, the corresponding antiderivative should be c times uppercase f of x. It is like the derivative, right? You know, this rule is same for derivatives. Let's say you have a function which is multiplied by a constant. When you get the derivative of that function, the constant is not influenced. The constant will remain as it is, right? You only get the derivative of the function. So that is same here in antiderivative. You just keep the constant in front and then get the antiderivative of the function. So these are the antiderivative. Let me put another word here. These are actually particular antiderivatives. All right, I will explain that later. So let me take this term down and specify it a little bit. This is actually, I'm sorry, take that out, take these two out. These are particular antiderivative. Particular antiderivative means you drop the constant. Keep that in mind. When I say particular antiderivative, you get particular antiderivative when you drop the constant. Let me note that. These are also particular antiderivatives because you just drop the constant. For the simplicity, we do that. In real life, we don't do it, but for the simplicity in this table, we just drop the constant. This is also a particular antiderivative. This is also a particular antiderivative. This, that. Both are particular antiderivatives. Okay, let me put a note on that. Let me use a different color on that. Particular antiderivative is the antiderivative we obtain after dropping the constant. Okay, as an example, (10x) is the particular antiderivative of 10. We just drop the constant. All right. So let me fill the table. And then let's say you have two functions like f of x plus g of x. In this case, you just get the antiderivative separately. This is also same as the derivative formula. In the derivative formula, let's say you have two functions. If you're gonna get the derivative of those two functions together, what you do is you just get the derivative separately, and then you just add the results. Right? It is same here. You get the antiderivative of simple f of x, which is uppercase f of x. When you get the antiderivative of the lowercase f of x, you get uppercase f of x, and the antiderivative of lowercase g of x should be uppercase g of x. All right. Then let's consider you are given the function x to the power n, where n does not equal to -1. N does not equal to -1. If n equals to -1, you will get 1 over x, which is not defined when x equals 0. So to avoid that situation, we just mentioned that n does not equal to -1. Right? So the antiderivative of this one should be x to the power n plus 1 over n plus 1. And then we took the case where n equals -1. Previously, you had x to the power n. If n equals -1, this will be 1 over x. Okay, let's consider antiderivative of that. The antiderivative of that one should be ln x absolute. All right. And then the antiderivative of e to the power x, which is same, e to the power x. That is also same in derivative. The derivative of e to the power x is just e to the power x. Okay, it happens here too. And then let's say you are given b to the power x. Antiderivative of that one should be b to the power x divided by ln b. And then let's move to trigonometric functions. Let's say you are given cosine x and sine x and secant x. If we have sine x, antiderivative of that one should be minus cosine x. If you have cosine x, antiderivative of that one should be sine x. And if you have secant square x, the antiderivative of that one should be tan x. All right. If you have secant x times tan x, secant x times tan x, the antiderivative of that one should be secant x. All right, so let me extend this table. and then just write inverse trigonometric functions. You know how to compute the derivative of sine inverse x, and the derivative of cosine inverse x, and the derivative of the tan inverse x, right? So here we are going to compute antiderivatives related to these inverse trigonometric functions. Let's say you are given 1 over square root of 1 minus x square, and the antiderivative of this one should be sine inverse x. Let's say you are given minus 1 over 1 minus x square. The antiderivative of that one should be cosine inverse x. And let's say you are given 1 over 1 plus x square. So the antiderivative of that one should be tan inverse x. All right, so let me extend this table further. I will get this out because that's not important. And then just talk about hyperbolic trigonometric functions. The first hyperbolic trigonometric function is cos x. The antiderivative of cos x should be sin x. And the antiderivative of hyperbolic sin x, that means sin x, should be cos x. All right, so that's it. There might be more than this much, more than this much of antiderivative formulas, but in this class we don't discuss everything. We only take commonly used antiderivative formulas. All right, so this is enough for this class. All right. So let me put a small note here. At the constant, I'm just saying that add the constant to these particular antiderivatives to get the general antiderivative. Add the constant to above particular antiderivatives to get the general antiderivative. All right, keep that in mind. All right, we have all the details and techniques. Now let's move to examples. Go to example number 1. Let me mark this as example number 2 because I gave the first example at the beginning. Example number 2. Find the antiderivative of the function f prime x equals hundred x square that satisfies f of 0 equals 100. All right. For now, you might not know how to use this condition. You might not know how to use that condition. When I'm solving the problem, I explain how to use that condition. For now, don't worry about that condition. Okay, for now, don't worry. So what I would do, I will just get the given function, which is f prime x equals 100 x to the power 2. Right. So this is the derivative of the f prime means the derivative. Derivative of the function is 10 x to the power 2. 100 x to the power 2, 100 x squared. Now you need to get the antiderivative. So you just introduce that notation, dx here, and introduce that notation, dx there. All right. So antiderivative of this function equals, 100 is a constant. In this table, you can use the first point. You can use the first point. When you have a constant in front of the function, you can just get the constant out and then get the antiderivative of the function. So you use that condition. You take 100 out and then integral sign x square dx. So that's the first step. All right. In the next step, you write 100, and now I'm gonna integrate x square. Let's go to the table. See, you have this formula, x to the power n. Okay, you can use this formula for any power except n equals -1. Except the case where n equals -1, you could use that one for any power of x. Here in our case, n is 2. Right, our case n is 2. So you write this to be x to the power 2. You see, go back again. If you have x to the power n, the result should be x to the power n plus 1 over n plus 1. X to the power n plus 1 over n plus 1. All right, and this and that. Now we use the same. Argument. So here you write x to the power 2 plus 1 over 2 plus 1. All right. And then you have to introduce that constant. Don't forget the constant. C is a constant. I write C is a constant. All right. So this should be 100 x to the power 3 over 3 plus c. That is actually f of x. F prime stands for the derivative. Let's say you are given function f. You get the derivative of that, and it will be f prime after getting the derivative. After getting the antiderivative of that, you can get the original function back. All right. So you get the function and then get the derivative of that. That will give you f prime. Antiderivative of f prime is just f. That means antiderivative of f prime equals f. You know that condition, okay? Antiderivative of f prime equals f. That's why we have this f right here from that. All right, so let me erase these unnecessary lines and circles. I'm going to post this note, so I will make sure that I don't put any unnecessary information. All right. Now, how do you find this constant? How do you find it? We have to get rid of this constant. For that, we could use this condition. It says f of 0 equals 100. Now I'm going to use that condition to get this constant away. We know that f of 0 equals 100. So you just plug 0 for x. That is, you plug 0 for the function above. So that means f of 0 equals 100 times 0 to the power 3 over 3 plus c. This is actually c. When you simplify the right hand side, you will get c. And this f0 equals c. Okay, now you consider these two. Lines. In first case, f0 is 100. The next case, f0 is c. The conclusion is c equals 100. Okay, now you solved it for c. Now the function should be 100 divided by 3. Let's say this is number 1, equation number 1. I write by 1, you write f of x equals 100 over 3, x to the power 3 plus c. Oh, sorry, c is just 100. All right, so this is the solution. Let's move to the next example. Example number 3. Give me a second until I check something. All right, good. Find f of x if f double prime of x is 12x to the power 2 plus 6x minus 4 where I put comma for where f of 0 equals 4 and f of 1 equals 1. Okay, so this is the given function to you. So you have to find f of x. What you are given is f double prime of x. All right. So what is this double prime? What is this double prime? F double prime is the second derivative. Okay, it's the second derivative. You have function f, you take the derivative of the function and then you take the derivative again. Okay. This equals the derivative of f prime x. the second derivative. You take the first derivative and then you take the second derivative, which is f double prime. All right. Now let's change this one into an integration problem. You know f double prime x equals, by this condition, you know f double prime x equals the derivative of f prime x. That is you could say f prime x equals the antiderivative of f double prime x. All right. F prime x equals antiderivative of f double prime x. In this case, you won't be able to get f of x at the first try. You won't be able to get this f of x at the first try. What you get is f prime x. In order to get f of x, you have to get the antiderivative again. So that's our plan. Okay, so here we are going to get the antiderivative twice. All right, let's go forward. F double prime x is 12x to the power 2 plus 6x minus 4 dx. Okay, here there are three functions. You know there was a formula for that. If I go above, if you have two functions, see, if you have two functions, you can just get the antiderivative of each function separately. In the same way, if you have three functions, you can get the antiderivative of each function separately. Okay, so I'm going to use that condition in this example. So I'm going to get the antiderivative of 12x square plus antiderivative of let me put I missed dx and antiderivative of 6x, and then let me put minus here. Antiderivative of 4 times dx. All right. Then you have to use another rule given in that table. The next rule says you can take the constant out from the integral sign. Then you have 12 times x square, the derivative of x, antiderivative of x square, and then you take 6. Then you take the antiderivative of x, and then you can take 4 out. You get the antiderivative of 1. For 1, I just put x to the power 0. Okay, for 1, I just put x to the power 0. I will explain why I put x to the power 0. Right, so concentrate here. I will explain this why in the next step. This means 4 times x to the power 0. That is same as 4. And then I use the power rule, x to the power 2, and I have x here and x to the power 0. All are powers of x. That means I have to use this rule. Again, I have to use that rule. And here I write 12x, here x square. If it was x to the power n, let me write this rule here because I can scroll up again and again. So I write that rule here. The rule says antiderivative of x to the power n should be x to the power n plus 1 over n plus 1. So this is the rule we have. This rule is very helpful. So you use that rule, and then here you write 2 plus 1 over 2 plus 1, and then we write 1, plus, and then we write 6, and then here x to the power 1, technically this is x to the power 1, so we write x to the power 1 plus 1 over 1 plus 1, here minus 4, you have x to the power 0, then we plus 0 plus 1, 0 plus 1 plus that constant. We use this formula 3 times. Keep that in mind. We use this formula here, we use that formula there, and we use the same formula here. We use it 3 times. And then we write equal and then write equal here 12 3 divided by 3, and then x to the power 3, and here we have x divided by 2, x to the power 2, here minus 4, x plus c. Finally, after simplifying this, we get 4x to the power 3 plus 3x square minus 4x plus c. That is our f prime x. Okay, that was our f prime x. Still not the end. We only got f prime x. What we need is f of x. That's what we need. So we have to work more. Alright, now I'm going to get the second antiderivative. Actually, we know f of x should be, the antiderivative of f prime of x. Alright. That means I'm going to get the antiderivative of this function again, which is 4x to the power 3 plus 3x square minus 4x plus c. I'm going to get the antiderivative of that function. Alright, again, like I explained to you before, you can just get the antiderivative of the function separately. I get the antiderivative of 4x to the power 3 plus 3x square dx minus 4x dx plus c dx. I split that integral into 4 separate integrals because there was a rule like that in that table. Again, I can get 4 out, which is a constant, and then I write that. I can get 3 out, x square dx, and I can get 4 out, x dx, and I can get c out, and I write x to the power 0. X to the power 0 is same as 1. Okay, if you have doubt why I got that, that is because x to the power 0 equals 1. Now I use the power rule again. You see the power rule here. Let me copy that. I can just keep it like that, so we can write it again. So we are using the power rule again. And then here what we get is 4 times x to the power 3 plus 1 over 3 plus 1. That is what we get from this formula. Then here 3 x to the power 2 plus 1 over 2 plus 1 minus 4 x to the power 1 plus 1 plus c times x 1 plus 1 0 plus 1 over 0 plus 1, and you have to have another constant which is d. Since I have used c already, I use the notation d for the constant. And I simplify this. I get 4 over 3 x to the power of 4 plus 3 here, 3 there. So you can cancel them. Then x to the power of 3 minus 4 here, 2 there. You can put 2x square and then cx plus d. So this is your f of x. I made a mistake here. The mistake is here you have 4 and here 3 plus 1 is again 4. You can cancel them, right? Here 4, there 4. So let me correct that. So this should be just 1. All right. Now I have the formula, the final formula. That is this. That is the function we have. Now you have to solve it for x and d. Okay, you have to solve it for x and d. For that you can use these conditions. Given condition. Those given conditions are, you are given that condition and this condition. You could use those two conditions to find the constants. All right, go down. You know that f0 is 4. You just plug x equals 0. When x equals 0, you get f0 equals 0 plus 0 minus 0, 0 plus d. All right. So that is d. f0 is d. At the same time, you know f0 is, from the initial conditions, you know f0 is 4. Then you can use that condition over there. f0 is 4. Let me write. We know that f0 is 4, thus d equals 4. Okay, then go to the next case when x equals 1. Okay. That is the next case where x equals 1. All right, when x equals 1, you plug 1 for x. f1 equals 1 to the power of 4 plus 1 to the power of 3 minus 2 times 1 to the power 2 plus c times 1 plus d. This equals 1 plus 1 minus 2 plus c plus d. All right. So this is c plus d, because 1 plus 1 minus 2 is 0. That is f of 1. At the same time, we know f of 1 because that's given to you. F of 1 is 1. You can write we know f of 1 equals, I'm sorry, what was the value? F of 1 equals 1. We know that is 1. Thus, one equals c plus d. You already know d is 4. That means 1 equals c plus 4. This 4 comes from here. And then c equals negative 3. Okay. Finally, we have the function. Give me a second. finally we have f of x equals x to the power 4 plus x to the power 3 minus 2x to the power 2. Our c is 3x, d is 4. So this is the corresponding answer. All right. So this was a long example because we had to find two constants because it was the second derivative. Since you were given the second derivative, you had to get the antiderivative twice. Let's move to the next example, which is example number 3. I'm sorry, it's example number 4. This is a real life problem which discusses about a rocket. A rocket lifts off from the surface of the earth, from the surface of the earth with a constant acceleration acceleration 20 meters per square second. Okay, part A of the problem. How fast the rocket be going after 60 seconds. All right, part A. Then part B, how far the rocket is from the earth after 60 seconds. All right, so those are the two parts of the problem. Let's move to the first part. There's a rocket lifts off from the surface of the earth. Let me make a small diagram. This is the earth. Okay, so this is a rocket which is right here. Okay, which lift off from the earth with the constant acceleration. The acceleration is 20 meters per square second. All right, the part A is how fast the rocket be going after 60 seconds. Now we have to understand the variables here. Variables are not explicitly given to you, so variables are hidden. You have to understand that. All right, it is asked the first. You have to find how fast it goes. How fast it goes. Fast means the speed. Okay, fast is the speed. Then you have to find how far it is gone. That means the displacement. Okay, these are the variables: speed, displacement, and then you know the acceleration. Okay, acceleration here too. So the variables are like that. Now you have to represent displacement by a variable. All right. Let the displacement of the rocket, give me a second, after t seconds is d. So we use d to denote the displacement. All right, d is the displacement. More than that, we also denote the speed by v. The speed of the rocket after t second is, we use v for that. By the way, let me introduce the independent variable in the previous case. Don't just write t, write it as d of t, because it is with respect to the time t. Okay, the displacement after t seconds, here the velocity, also the speed after t second. Okay. Now I denote the acceleration. Let the acceleration is at. Let me add a little bit more to that. The acceleration after t seconds is a of t. All right. So you have all the variables now. You have dt, and you have vt, and then you have at. All right. Okay, good. Let me make a small change here too. Let me get this little down to the next line so it's clear now. Right. Now we have to write the physics behind this. You write the physics behind this. You know, acceleration is rate of change of the speed. Okay, acceleration is rate of change of the speed, and the speed is rate of change of the displacement. First part of the question talks about the speed. So let's write something by combining acceleration and speed. Okay, combine something with acceleration and speed. You have to combine acceleration with speed. The formula here is at equals d over dt vt. That means the acceleration is rate of change of the velocity. All right, you know this condition. Acceleration is rate of change of the velocity. Right? Then if you need to find the velocity or the speed, in our case, that is the antiderivative of the acceleration, because you learned that. right? You learned that because acceleration is the derivative of velocity. Antiderivative of the acceleration is velocity. All right, something like this. Let's say you have vt, which is the velocity. If you get the derivative of that, you get the acceleration. If you get the antiderivative of the acceleration, you get the velocity or the speed. All right, so that goes like that. Right, now you know the acceleration. Now I'm going to integrate that. Acceleration is given to be how much? It is 20. Acceleration is 20. So you're going to take that condition. So you write 20 here. You're going to integrate 20 with respect to t. You know 20 is a constant. You can take 20 out. Then here you have t to the power 0 dt. T to the power 0 is just 1. Now you use the power rule as explained in that table. So this is t to the power 0 plus 1. Here 0 plus 1 plus a constant. All right. If you simplify this, it should be 20t plus c. That is v of t, the velocity of the rocket. All right. Actually, this function or this formula does not describe the velocity explicitly because it has this unknown. This c is unknown. C is a constant. As long as this constant is there, you won't be able to explain the physics behind this situation. So how do you find c? You have to find c. You have to find c. That's a question. You have to find c. For that, you have to use a condition, initial condition actually. In the previous class, can you remember you were given two conditions? This is one condition given, there's another condition given. Both are conditions given to you. In the current example, you are not given conditions, but you have to find them. You have to find them. Okay, you have to find a condition with the velocity. All right, so let me explain that. When the rocket is on the ground, this rocket is on the ground, what is the velocity? The rocket is on the ground, the velocity is 0, right? When the rocket is on the ground, the velocity is 0. All right, because that is not started yet. When it's on the ground, the velocity is 0. The time is also 0. That's the beginning, just start of the rocket. The rocket doesn't move, so the velocity is 0. The time is also 0. So I'm going to use that condition. Let me write this because you can understand if I write it. Give me a second. Yes. At the beginning, the rocket was at the rest. That is when t equals 0. That's the beginning. When t equals 0, v of 0 was 0. The velocity was 0. So I'm going to use that condition here. All right. I'm going to use that condition. Now I'm going to consider where t equals 0. When t equals 0, I have v0 equals 20 times 0 plus c. This is c. v0 is c. At the same time, we know v0 is 0 too. Okay, we know that condition, and then we know this condition, which is right here. Okay, so we know these two conditions. Okay, that means c should be 0. This is 0. All right, so that's convenient. Now you know c is 0. Thus, the velocity should be 20 t. Now you have to find the velocity after 60 seconds. How fast the rocket be going after 60 seconds? The speed of the rocket after 60 seconds. That means the t is 60. Okay, when t is 60, you get v60 equals 20 times 60, which is 1200 meters per second. Okay, so that is the solution for part A. And then go to part B. In part B, you have to find the question is how far the rocket is from the Earth after 60 seconds. It's asking how far, that is the displacement. Right? Now you have to find d60. You have to find d60. That is the displacement after 60 seconds. Alright, for that you have to get the derivative of Vt again. You know that Vt is the first derivative of the displacement. We know Vt equals the first derivative of the displacement. Thus, dt is the antiderivative of Vt. Okay, you know Vt already because you have found that, which is 20t. You're going to get the derivative, antiderivative of 20t. 20 is a constant. You can take 20 out and then get the antiderivative of t. Here also you are using the power rule. This is t. This t is to the power 1. So you write t 1 plus 1, 1 plus 1, and then you put a constant, which is d. Give me a second. All right. Simplify further. So this equals 20 divided by 2 is 10 t square plus d. Give me a second. I don't use the notation. I don't use the constant d because it might be confusing to you. You have already used d here. So you have already used d here. Let me use a different notation. I use k for that. Okay, k for the constant. This is dt. Again, you have to find what this k is. Okay, you have to find k. Let me write that. You have to find k. Have to find k. For that, you have to use again an initial condition. Go to the rocket. In this rocket, now we have to find the initial condition with the displacement. Okay, at the beginning, the rocket is at rest here. The rocket is at rest here. That means the displacement is also 0 at the beginning. Like velocity, the displacement is also 0. So you write at the beginning, let me copy, no, I'll go back. At the beginning, the displacement is 0. The displacement of the rocket is 0. That is d0 equals 0. All right. Now just plug 0 for t. When t is 0, you write d0 equals 10 times 0 to the power 2 plus k. So this is k, d0. All right. Here d0 is k and there d0 is 0. All right. The conclusion is k equals 0. Thus, k equals 0. So you have dt equals 10t square. Let me put this as equation number 1 and let me put this as equation number 2 by 2. Let me write by 2. By 2 we get dt equals that 10t squared. All right, now go back to the problem. You have to find how far the rocket is from the earth after 60 seconds. Okay, you have to find d at 60th second. At the 60th second. So that means you have to find d 60, which is 10 times 60 square. 60 square is 3600. This value should be 36000. That many meters away. That is d60. So this is the displacement of the rocket after 60 seconds. All right, so this is the end of the section. Thank you very much.